Hello, ladies and gentlemen. Mr. Donnie here again with some chemistry problems. Looking at the 8.1 problems, chemical bonds, Lewis symbols, and octet rule, and 8.2 ionic bonding. So starting with question number 1, of the ions below, only blank has a noble gas electron configuration. So the noble gas electron configuration, talking about having 8 valence electrons. So which one of these things would have 8 valence electrons? Well, let's check it out. Sulfur has 6 valence electrons normally, and it is a -3 charge. That means it gained 3 electrons, so it's got 9. That ain't going to be it. Oxygen also has 6. The +2 tells us that we lost 2 electrons, meaning we got 4. Iodine has 7. Positive charge means we lost 1 electron, so we only got 6. Potassium, we had 1 valence electrons. That minus is saying that we gained another electron, so it has 2. So hopefully E is our answer. Chlorine has 7 valence electrons. That -1 charge tells us we gained an electron, and that means we have 8 valence electrons. So choice E. Which of the following has 8 valence electrons? Kind of like the last question, huh? So to do this, first, why don't we look up how many has 8 valence electrons? Titanium has 4 normally. Mr. Johnny, where'd you get that from? Wrong one right here. Titanium, where's it at? Right here. No, wait, Ti, over here. Totally lied. It's got 1, 2, 3, 4 valence electrons going on. All right. And then it lost 4. So now it's down to its full shell of 8. Krypton, noble gas, has 8. Chlorine, minus means it gained 1 electron, started with 7, gained 1 more, so it has 8 now. And a plus was 2-8-1. That +1 means it lost that last. Look at that, all of them have 8 valence electrons. 3, which of the following would have to gain 2 electrons in order to achieve a noble gas electron configuration, right? So we're talking about 8 valence electrons, right? So if we take a look, oxygen has 6. Strontium, where's that at? Strontium's over here. So it has 2. Sodium has 1. Se, where is that one at? Se, selenium, has 6 valence electrons. Right? And Br is right over here. So it has 7 valence electrons. Which one would have to gain 2? Well, oxygen and selenium would have to gain 2 in order to have 8. Question number 4, kind of a definition question. Lattice energy is blank. I'll ruin it for you. It's choice A. The energy required to convert a mole of ionic solid into its constituent ions in the gas phase. So we're talking about going from a solid compound and separating them completely into their separate ions in the gas phase. So that is the lattice energy. So this is going to be really positive when you think about it, because these two things are really attracted to each other because of the opposite charges, right? We got a positive and a negative, so they would be attracted to each other. So in order to separate them, you're going to have to put in a lot of energy to break them apart. All right, I like this question. This is a Born-Haber cycle kind of problem, showing you what's going on. All right, and it can be intimidating at first, but just take a second, and figure out what's going on. They numbered the arrows for you, so this is where we're starting, right? So we're starting with solid potassium and half an F2 gas molecule. All right, and what changes is the potassium goes from a solid to a gas. So what do we call that step? Well, that's the heat of sublimation. So delta H for sublimation of K, because K is going from solid straight to a gas. That's subliming. Second arrow, what's going on here? Well, we start with half an F2, and then it shows just F by itself. So we got rid of one of those Fs. We broke a bond. We call that the bond dissociation energy. And it's going to be the bond dissociation energy for a FF bond. So we broke that so that we got F by itself. Next stage, step 3. All right, what changed? Well, potassium became positively charged by losing an electron. All right, isn't there a term for losing, like taking an electron from an element in its gas phase? It's called the ionization energy. So now we're looking at the ionization energy of potassium. Step 4, what happens is that electron is gained by the fluorine. Right, so fluorine gains an electron. What do we call that energy? That is the electron affinity. How much energy was released by that process? In this last step right here, we have the two oppositely charged ions coming together to give us an ionic compound, an ionic solid. That is the lattice energy. Now, take a look at how much that is. That's a really big arrow. A lot of energy is released when those oppositely charged ions come together, which is why it takes so much energy to separate them. It makes sense. They're oppositely charged. They're attracted to each other. They're like magnets wanting to be stuck together, right? These steps where we went up are all investing energy. It takes energy to sublime the potassium. It takes energy to break apart the fluorines. It takes energy to remove an electron from the potassium. And then up here, all right, the electron being gained by fluorine is favored, right? That's why it goes back down. And then the two oppositely charged ions come together. That's favored to down here. Now remember, 1, 2, 3, 4, and 5 should equal 6. Right, that's the overall change. Hess's law, we can look at each of the steps, add them all together, and it should give us the overall change. So number 5 says which energy change corresponds to the electron affinity of fluorine? Well, that would be step 4, right? So choice C. And 6, which energy change corresponds to the first ionization energy of potassium? Well, that would be choice D, right? Arrow number 3. 7, the electron configuration Kr 4d10 represents blank. All right, there's a couple of ways that you can solve this kind of problem. The easiest is probably just go, well, how many electrons does Kr have? It has 36. And then we add 10 more to it. So we must have 46 electrons, which means we got, we've just got to look at each one of these. So now Sr normally has 38. That plus 2 means it lost 2. So it only has 36. Can't be A. Tin, Sn, normally has 50. How did it get that positive 2? Well, it lost 2 electrons, so it has 48. Can't be B. Te, tellurium, normally has 52. That positive 2 means that we lost 2 electrons, so we only got 50. Can't be C. Ag, I'm running out of room, normally has 47. It became positive 1 by losing 1 electron, so it has 46. Hey, isn't that what we wanted? Awesome, but let's check Rb. Rb normally has 37. It became positive 1 by losing 1 electron, so it has 36. So not what we want. Mr. Johnny, where'd you get all those electrons from? Just off the periodic table. Remember, protons equals electrons, so the atomic number for everything is also how many electrons it has when it's neutral. 8, Fe plus 2 ions are represented by blank. All right, well, Fe normally has a configuration of Ar, and then we fill the 4s2, and then we go into the 3d sublevel, and there are 6 in there. Now, the question is, well, where do these electrons that are getting lost come from, right? Well, you might think, well, let me take them from the d sublevel because I added them last. Wrong. All right, the electrons are going to be lost by the outermost principal energy level. So the 4th energy level is where we're going to lose the 2 from. So we're going to lose those 2. So the Fe plus 2 is going to equal Ar. And then we're left with just 3d6, which would be choice C. Chloride ion of which of the following metals should have the greatest lattice energy? All right, things that are affecting lattice energy are going to be the charges. Wait, whoa, forward. Sorry, guys. between the atoms. So the greater the charge, the greater the lattice energy, the greater the distance between the atoms, the lower the lattice energy. This makes sense. The closer you can get them, the more energy they're going to release. The more strongly they're going to pull onto each other. So we're looking at this. They're all bonding with chloride. So we're looking for something with the greatest charge and the smallest atom. So let's take a look at potassium, rubidium, sodium. They're all in group 1, right? We're looking at all of these things right here. And they're all combining with chlorine. So which one is going to give us the greatest release of energy? It's going to be the smallest one, because that one will let us get closest to the atoms closest together, right? If we got these two atoms, right, and we got the nuclei there, the smaller they are, the closer they can get to each other, right? That one's going to get a lot closer than if we had the two large ones bonding with each other, right? Sorry, I can't help myself. It's a face, right? He's a happy guy. Anyway, so since lithium is the smallest one, it can get closest with the chlorine, which is going to release the most energy. So lithium is going to be our final answer. All right, guys, hope you found that helpful, and I will see you in class.